Find the nominal moment in pounds-inches, which causes the concrete in the beam to crack. In this problem, an inverted T-beam is reinforced with 8 number 9 reinforcing bars of steel. The dimensions of the beam are provided in the figure. The compressive strength of the concrete and steel is provided, as well as the Young's modulus and the moment of inertia for the uncracked transformed beam. The concrete in the beam will crack when the applied moment causes the beam to exceed its modulus of rupture. In this equation, Fr represents the modulus of rupture. For this problem, we'll use the units of pounds per square inch. M represents the applied moment. This is the variable we're solving for. H represents the total height of the beam, and variable y sub ut represents the depth to the neutral axis of the beam. Variable I sub ut equals the area moment of inertia of the beam. The subscript ut refers to the uncracked, transformed state. We'll rearrange this equation to solve for the applied moment, m, and change the at-most sign to an equal sign. The modulus of rupture for concrete equals 7.5 times the square root of the compressive strength of concrete in pounds per square inch. This equation returns a modulus of rupture with the units of pounds per square inch. After plugging in the given value for F prime C, the modulus of rupture equals 530 pounds per inch squared. The uncracked transformed moment of inertia is given in the problem statement as 12,622 inches to the fourth power. The height of the beam, h, can be determined by adding the 15 inches and 5 inches shown in the figure. The last variable we need to solve for is the depth to the neutral axis, y sub ut, which equals n times a times y summed for all parts in the cross-section divided by n times a summed for all parts in the cross-section. In this equation, the variable n represents the stiffness ratio, and variables a and y represent the area and depth to centroid, respectively. We'll divide the cross-section of the beam into 3 parts, where part 1 is the concrete web of the beam, part 2 is the concrete base of the beam, excluding the rebar, and part 3 is the rebar. The stiffness ratio, N, for part I equals the Young's modulus of the part I divided by the Young's modulus of a reference material. We'll use concrete as our reference material and add a subscript C to the denominator. This makes N for parts 1 and 2 equal to 1. N for part 3 equals the Young's modulus of steel divided by the Young's modulus of concrete. The problem statement provides the Young's modulus of steel as 2.9 times 10 to the 7th pounds per inch squared. The Young's modulus of concrete equals 33 times the unit weight of concrete raised to the 1.5 power times the square root of the compressive strength of concrete, where the Young's modulus is in units of pounds per square inch. The unit weight of concrete is in units of pounds per cubic foot, and the concrete compressive strength is in units of pounds per inch squared. Unless the problem states the concrete is lightweight, a simpler equation is used, which assumes the unit weight of concrete is about 144 pounds per cubic foot. We'll use this second equation. After plugging in the unit weight of concrete, the modulus of elasticity of the concrete equals 4.03 times 10 to the 6th pounds per inch squared. This makes the stiffness ratio for part 3 equal to 7.196. Next, we can compute the area for each of the 3 parts. From observation, the area of part 1 equals 15 inches times 12 inches. The area of part 3 equals 8 number 9 reinforcing bars times 1 inch squared for every number 9 reinforcing bar. The area of part 2 equals 24 inches times 5 inches minus 8 inches squared. Next, we'll simplify the area calculations. To simplify a future calculation, we'll pretend the area occupied by the rebar is occupied by concrete at its normal stiffness and also occupied by steel, except with a Young's modulus reduced by the Young's modulus of concrete. The depth to centroid, y, for part 1, measured from the top of the beam, equals 15 inches divided by 2. For part 2, y equals 15 inches plus 5 inches divided by 2. And for part 3, y equals d, which is 18 inches. Now we can return to our equation for the depth to the neutral axis for the beam. Next, we'll write out the summation, plug in the variables, and the depth to the neutral axis in the beam equals 12.42 inches. Next, we'll plug in the variables to find the moment which causes the beam to crack. And that moment equals 8.825 times 10 to the 5th pounds inches. When reviewing the possible solutions, the answer is C.